remark that I think I didn't emphasize, it's not very important as well, but it's worth knowing. I said that if you have a simple group, then you have a unique up to scale invariant bilinear form on it. I mean, we have one, which is the Killing form, but actually it is unique. And the reason I said is that if, whenever you have two invariant forms, whenever you have two forms, there is some non-trivial linear combination of them, which is which is degenerate. A thing we cannot have on a simple group because the radical is always an ideal. So is this clear? This is very easy. So someone wants to give the proof of that? If I have two forms on a vector space, A and B, independent, I claim linearly independent forms. I claim that there is a linear combination which is degenerate. So I can think about matrices, right? So after normalization, I can look at all these linear combinations, and I can look at this determinant of that one. So this is a polynomial by lambda over the complex numbers. Okay, and now consider the following problem. So I'm fixing now, fix a Galois extension. Finite Galois extension. If you want, already very interesting case, for all this consideration, C over R. Non-trivial at all. So, but we can deal with slightly more general situation. By the way, everything I'm saying actually has, I mean, up to some rather easy modification. I mean, I can take this finite away. And then the Galois group, G here, will be a Galois group. At least for the first part, I will not use other groups. I mean, I will not use algebraic groups. I will use other groups. Gal. So, of course, it's a finite group in this situation, and if I remove the finiteness here, this will be some profinite group. So the theory could be taken for profinite groups as well. But let me not go there right now. Maybe I will remark at some point on the needed modification. Now, given an affine, I will walk over affine varieties. Actually, the theory that I'm about to expose is also could be derived on over quasi-projective varieties. But I don't need it. It's slightly easier to work with an affine variety. V over F. So it is defined over F. We may consider the affine algebra F of V and its extension. I can extend the scalars, and in that case, it's just E of X. Polynomials, regular functions. Possibly, I can find V prime over a affine variety such that V is not V prime over f, but is over E. As a variety over E, they are the same, but over f they are not. For example, I will not write it down, we've seen, it comes a lot in group theory, take two different real forms of one complex algebraic group. Take SO11 and SO2. Take S1 and R star. These are two forms of the complexification of these two real varieties is the same. But they are not equivalent over the real. Since I'm working on affine varieties, an equivalent formulation is that FV is not isomorphic as algebras now, as an F algebra. I can't find such an isomorphism, but I can find an isomorphism of these E algebras. So V prime, I would say, is another form, another F form of the E variety V. Okay? V is an F variety, is an F form of the E variety V, the extension of scalars to E, and V prime is another. Of course, it is another because it is not isomorphic. I'm considering the problem of finding now, this is the descent problem, is finding all forms, all F forms of a given variety up to F isomorphism. Okay, so this is the problem that we're seeking. So we want to classify all descents, or all F forms of V up to F isomorphism. Let's give the name, maybe D V. This is not a standard name. The standard name, and this will appear. This is equivalent to some non-abelian first cohomology group, cohomology set, which I'm about to explain. So this name is temporal. Usually we use the homological symbol. So somehow, but our situation is a bit non-symmetric. I didn't take an E variety. I could, and start thinking of all its forms. I took an F variety, and this is the main point somehow, and I want to look at its brothers. Okay, so this is a legitimate thing to do, but now somehow it is not balanced the way I'm looking at, and this will come. We'll see this coming, but it's useful to do this.
I don't understand the difference. So
Between what?
between what you said. I mean, taking the variety over F and
It's
extending
just a
it.
point of view. It is a difference in point of view. I mean, I can start with, you can start with a complex variety, and now ask, sorry, can I find real forms for it? Sometimes you don't, sometimes you do. If you do, classify them all.
Okay.
Somehow it will come up useful to fix one and think of others as the formation of this one.
Because you know that one exists.
If you do know that one exists, then you can think of the others. This is, in some sense, this is what we did at the previous hour. You took a split form, and you deformed it a bit, in a certain way. I mean, which was not a continuous deformation, but we didn't deform it, and this deformation gave us another form, right? If to those of us who are familiar with theories of deformations, many times deformations comes about by means of H1. H1, somehow, if you have space of deformation, H1 is a tangent space to that space at a given point. This is some sort of philosophy. And indeed, this is something, here we will not have continuous deformation, so everything is sort of discrete, but we will have a finite theory of deformations, and it will come up by a certain H1. And I hope to be explicit about it. Maybe we will not get to the chronological situation today, but now I want to consider, but we will certainly prepare the situation. Now I want to consider the algebraic geometric problem. Okay, so is the problem understood? Okay, observe. So here's our. The thing is that G acts on EV and extending the reaction on E. So E, of course, sits. This is an algebra with an identity with 1, and these are the constant polynomials on V. And G act on it because, I mean, since V to begin with was an F form. Okay, so V is defined by some polynomials. So this gives me a natural action on this one. So this is not an abstract algebra. This is an algebra of polynomials, E polynomials, and I can change I can take the Galois automorphism of the field and change and act on the polynomials, on the coefficients of those, right? So. So if I would just take an abstract point of view, if I would start with a variety without a real form, without an F form, then I would not have this well-defined Galois action. If you want the ring of function of an absolute variety, well, if you think of your variety as embedded into En, then yes. Then you could act on En if it is embedded in some invariant form, invariant respect to Galois. A priori, also, even if it is embedded in En, it is not clear that it is embedded in such a way that when you apply that it is invariant to the Galois action. Maybe if you take in the complex plane this point as your variety, its image under conjugation will be another point. The variety is not stable under the action. Okay? Somehow the fact that I took to begin with an F variety guarantees that I do have such an action. Okay, so I guess I emphasize this enough. So here's a proposition. I will have, again, in the future, we will have a chronological description, but now I want to describe this space of forms as a space of actions of G on EV as a bar extending the Galois action of G on E. So this is the algebraic. I mean, now I have to explain why these two things are isomorphic naturally, but then we'll have a specific is the formulation clear?
The isomorphism is in what sense?
As a set.
Okay.
But it will be explicit. I mean, I'm not writing the right form of proposition. Proposition is, let me explain.
Like there's a one-to-one correspondence.
There is a one-to-one correspondence which is very explicit. But as we've seen, started with an V with an F structure, actually have an action here. The embedding of E inside here is canonical. It is the fact that this is an E algebra with unit. So the fact that this collection has nothing to do with, maybe I should denote B. Let's call this B. This is an affine algebra, and this is a general claim. This is an affine algebra with spectrum V, defined over E, and I claim that all forms of it. Now I took the other perspective, the symmetric perspective. I didn't start with an F structure on V to begin with. Take V as an E space, and I claim that all the forms of it are given by such extensions of the Galois action. And this is pretty much straightforward, but I mean there are things to verify. Maybe I guess that by exposing it, I explain why I have this map. If I did start with an F structure on V, I would get the natural Galois action on the algebra of polynomials on it. Clear. I want to explain this, and I guess I will not prove that the ones that I'm describing are mutual inverse. This I leave to you, but I really need to explain how, given such an action, I'm cooking for you a real structure. I need to show that I can find A, which is an F algebra. This will be F of V, right? Which is finally generated as an F algebra, non-nilpotent. So it's an affine algebra, it will have a spectrum, and this spectrum is supposed to be the F form of my guy V. So, otherwise put, this A, the complexification of this A, the E-ification of this A should be the construction of such an A will be the latter over here. Okay? Is this understood? And again, I leave it to you to see that if I'm giving you this arrow, those are mutual inverses. So now I explain what to cook this A. Maybe you see it right away. If you start with this guy V over F, you have FV. How do I find this is my A to B, but I only know E of V. How do I find F of V? In it, the fixed point of G. So there is A, which is the fixed point of G in B, and action is given. We'll do the job. We'll do it. Now I have to prove it. So I need to show, first of all, that A is a finely generated F algebra with no midpoint. The last is very easy. No midpoints, why? Because B has no midpoints, right? It's a subalgebra of algebra. So finite generation, this is a classical argument. It has nothing to do with this setting. So I claim that if you have a finitely, okay, I'll make a remark. I want to make now. E over f finite implies that B is finite generated F algebra, right? And to take B is finite generated as an E algebra, add some generators to E over F, to this E over here, and you have it. So the claim here is, as Nilpotec is not a problem at all, the finite generation of A has nothing to do with E. Now we have B, which is a finite generated F algebra, some group, finite group acting on it is G, and the fixed point of that group is a finite generated subalgebra. So this is theorem number 1 in invariant theory, if you know, if you ever. So this is a very basic fact. I will prove it for you, but probably you've seen it before. So fact to be proven. But I'm summarizing what are the properties that I'm using actually. B, finite generated F algebra. G, finite group of algebra automorphisms. Then A, which is BG, is finite generated as well. Finite generated F algebra.
Let me address some equivalence relation on the action of geometry, the command there.
No, because this is very explicit. This is the action on B itself. I don't have isomorphism in it. Okay, it's not. I fix B. It's not you look at all as when I expressed this problem. Well, where did I find B? Oh, no, here. So here I wanted all things up to an isomorphism. But now I fix one model algebra and I'm acting on it. Okay. Now, so this is an accelerated algebra. Let's solve it. Let's do it in brackets. It's short and easy and very nice. Someone saw it before? Someone saw it. Fix B1, I don't know, to Bn, gen generators to B, again, as an F algebra. Now I'm constructing polynomials. Pi will be the product of the monomial. I'll give myself some space here. Pix. So this is something in. Start. I'm constructing polynomials in Bx. X is one variable. For each I, I'm getting a polynomial. And this is, basically it's a polynomial for which Bi is a root, but I forced invariance on it. So I need to have x minus Bi factor, but I will take product of this over all g's, trigeminal. And this is some, well, I is fixed here. So I have alpha ij, x to the j. Some finitely many coefficients here, I'm seeing. Pi is 0 because 1 is one of the g's that I see. And Pi's are all, as you see, if I apply g to Pi, I get the same. So Pi is in AX. So it means that alpha and j are ordinate. So I have those finitely many elements of A, and I can take, I don't know that A is finite generated yet, so I'll take the thing C that is generated by those. Alpha and j. Is a finite generated F algebra. Now what can you say about B?
B is an extension.
B is an extension.
Like a
Just
extension
F,
is-
just to see it. So again, the order of things. B is an extension. B extending A, extending C. This is finite generated F algebra. This is a finite generated F algebra. This I don't know. What can you say about the extension B over C?
It's algebraic. It's algebraic and what? Whatever you want. B over C.
Those are not field. And
Oh, sorry.
right. So B is finite generated over C as a model. Okay, finite generated. Model. Finite generated as a model over C. Right? I mean, it's certainly generated by the BIs as an algebra, as an F algebra. So it's generated as a module by the BIs and their powers. But whenever I have a too high power, I can reduce it using those coefficients, right? If J goes here from, I don't know, 1 to nj, ni. Okay, this is you've seen. So this is a finite generated model over that. It means that this is Noetherian. C is Noetherian. So I get that A is finite generated as a model over C as well. And C is finite generated as an algebra, so A is finite generated. So this is this fact, and we get 1. I didn't try to. I forgot. So what is left to prove?
That E tens over 8.
Yeah. So 2. A tensor of E of B equals E tensor F A. Right. So again, this is a very, very general fact. B, now this is not about algebra. B is an E vector space. G, let me recall now that it's the Galois group of this. So I'm having this finite extension. G is the Galois group, and I'm having this action. So G act on B by they are called conjugations. I mean by this that the G of, so I'm having an action on this vector space, and it corresponds, of course I'm having an action of scalar multiplication from elements of E on B, and they're compatible. Maybe, this is not a standard terminology, so maybe in a compatible way. I'm defining it in any case in the next line. G of EB, obvious notations, is G of E. Like conjugation of alpha times a vector is the conjugation of the vector times, or to go to the scalars times conjugation of the vector, right? G of E. If you want, I'm having an action of a semi-direct product. G semi-direct E. This is not G semi-direct E. This is not well defined, or it's not a classical. But it is not. This is a semi-direct product of a field with a group. Whatever. And I'm having a compatible action. This kind. Okay, so the fact here is not stated yet. Assume this is the case, but this is what I need. I don't need the algebra structure on B. Then B indeed is, or maybe A now is, let me define it to be BG. Then B is E tensor of F with A. Okay, this is what I need. So just take the right generality of things. So why is that? So maybe let me take let me write the here. Let U be any finite dimensional F or E? F vector space. Here's, before proving it, let me claim a general claim. And M, let it be the endomorphism of U as an F vector space. Then I claim that B, this is a general fact about E vector spaces, complete generality. This has nothing to do with the Galois action. Home M. And this, tell me that you agree with this. But this is home. Now, what is the endomorphism of U? U star tensor U, B, which is the same as U tensor F. F endomorphism, right? With home M. Okay, so far so. I want to write down this formula. And now specialize to U is E as an F vector space. And M, well, let me write what M is here. M is the endomorphism type, right? But what is the endomorphism of E as an F vector space? Someone knows?
Field. Field.
E is a field. Forget it. Think of it as an F vector space.
B over M.
Sorry?
You wrote B equals home of M and B. How is B and M model?
M,
How is B and M model? M is just the matrices N by N over F, right?
what do I mean by this? This is something what I wrote in my notes. It's okay in the case that I want to consider, but
Usually you just define the function so it's injective.
sorry.
The usual proof is just define the function from E tends away to B and show its projection.
Do you prove what?
That's what I want to show, that B is isomorphic to E tends away.
The fact.
You prove non-defect or you?
Yeah, I'm proving the fact. Yeah, maybe I'm doing too much noise here. Let me give you a main ingredient and try to figure out what I want to say on the way, or you do it for me. But there is something which is, in any case, you should use. So let me go back to it in a minute. Consider the group algebra. Over E. EG. So I want to claim that there is a natural EG act on E naturally. So that this is supposed to be my M in notation over there, but maybe I should skip some line. But in any case, the claim is that, well, E act on E linearly, this is not a problem. Also G act on E F linearly. So EG both act on E F linearly. Right? And I claim that this map is injective. Is injective. Why? So this is independence of characters. This is classical thing. Galois elements are independent over E. Is injective. And also surjective. Why?
Same dimension.
This is by dimension. So the dimension of E over F is some number n, and the Galois group is of the same number n. So this is n squared, and of course this is n squared. By dimension, hence isomorphism. And okay, now let me write down in the line as I wrote it, and then try to fix. I copied, I stole it from somewhere, and please check carefully. basically I want to claim that is EG. This makes sense. This is the same as on. I mean, I'm looking at EG maps from here to there. In particular, I'm looking at E maps from here to there. So they are the image of one guarantees everything. So this is the same in particular as FG map from here to there. So and the image of one should be in particular a fixed point. So this is the same as BG. That is A. And I guess so. The way I actually put it is incorrect. But the moral of the thing is that this guy over here is the same as this one, and tensoring with E should give me. Oh, this will be B. No, it's yeah. Tensoring with this guy with E over F, as in here, should give me B. And there is something to fix here, and of course I cannot do it.
But I just think that in this special situation,
Yeah, I shouldn't
the
have.
B is an M module.
The
But
B
if
is
you-
an F model, but
if you
yeah.
take any finite dimensional F vector space, then there's no natural M structure on B. But if in this case, I think it's
Yeah. Okay. What is time?
26.
26. Okay, so I guess it's good or not, it's time to stop. But let me summarize it for you because this is very important. So by now I'm having, I want to look at all the descents of V from E to F, and I know this. So my task at the next lecture will be to understand this collection. And for this we'll use non-abelian cohomology, and I will expose the general theory as well as the description of this guy. It's quite cute and also very powerful. And now we'll finish.